Let me ask you something. When you were a child, maybe 7, 8 years old, did someone ever hand you a magnet and hold it near a nail? And the nail just jumped, not slowly, not reluctantly. It jumped like it was alive. I remember that feeling. And here's what's remarkable. I never fully lost it. Not after studying physics for 50 years. Not after working on the Manhattan Project. Not after winning a Nobel Prize. That little tug between two pieces of metal, the fact that something can act on something else across empty space, that is, to me, one of the most astonishing facts in all of nature. And today, I want to tell you about the force responsible for almost everything in your daily life that isn't gravity. The force that holds your atoms together, that lets you see, that powers every light bulb and motor you've ever used, and that, if you understood it completely, would feel more like magic than any trick a human has ever invented. I'm talking about electromagnetism. Now, I want to be honest with you from the start. I'm not going to give you a watered-down version of this. I'm also not going to drown you in mathematics, at least not yet. What I want to do is take you on the same journey I took, step by step, from the simplest observations to some of the deepest ideas in physics. And if at the end of this you feel a little confused, a little dizzy, a little like the world is stranger than you thought, well, that's exactly what's supposed to happen. Let's start with what we actually see. Two kinds of phenomena, apparently separate, that turned out to be the same thing in disguise. The first, electricity. You rub a piece of amber with fur. The ancient Greeks knew this, and suddenly small bits of leaf or feather are attracted to it. Ben Franklin flies a kite in a thunderstorm and shows that lightning is just a big electrical discharge. By the early 1800s, scientists had learned to store electric charge in Leyden jars to make sparks, and eventually to make steady currents flow through wires. Volta builds his pile, the first battery, and suddenly electricity isn't just a party trick. It's something you can control and direct. The second phenomenon, magnetism. Lodestones, naturally magnetic rocks, have been known for thousands of years. Chinese navigators use them for compasses. Magnets attract iron. They have a north pole and a south pole, and unlike charges, you can never separate those poles. Cut a magnet in half, and you get two smaller magnets, each with its own north and south. It's maddening, actually. It's as if you had an object that was always heads on one side and tails on the other, and no matter how many times you cut it, each piece still had both sides. There are no magnetic monopoles, no isolated north without a south, and we've looked hard. Now here's where it gets interesting. In 1820, a Danish physicist named Hans Christian Ørsted is giving a lecture, or so the story goes, and he notices something. When he runs a current through a wire and holds it near a compass needle, the needle deflects. The wire is not a magnet. There's no iron in it, but the moving charge in the wire is making the compass needle move. Electricity and magnetism were talking to each other, and nobody had expected that. Then Faraday, Michael Faraday, a bookbinder's apprentice, who became one of the greatest experimental scientists who ever lived, takes this further. He asks the reverse question: if a current makes a magnetic effect, can a magnetic effect make a current? And the answer is yes. But only if something is changing. A steady magnet sitting next to a wire does nothing. But move that magnet, or change the current in a nearby wire, and suddenly a current appears in the second wire, as if from nowhere. This is electromagnetic induction, and it is the principle behind every electrical generator, every transformer, every power station on Earth. So we have two phenomena, electricity and magnetism, that turn out to influence each other, that are linked in a deep and beautiful way. And the question becomes, what exactly is the mechanism? What is it that reaches across space between the wire and the compass needle, between the moving magnet and the current it induces? The answer to that question is one of the greatest intellectual achievements in human history. And it came from a man who, unlike most physicists, thought not in equations first, but in pictures, in lines, in fields. Let me introduce you to the idea of a field, because this is the central concept, the one that makes everything else make sense. When you hold a magnet near a piece of iron, and the iron starts to move, your instinct is to say, the magnet is pulling the iron. And that's fine as far as it goes, but the physicist asks, how? The iron and the magnet aren't touching. There's nothing between them but air. What is the mechanism of the interaction? Faraday's insight, and it really was a stroke of genius. was to say, look at the space around the magnet, not just the magnet itself. Take some iron filings, sprinkle them on a piece of paper, and hold a magnet underneath. The filings arrange themselves in beautiful curves, looping from the North Pole to the South Pole, curling around in a pattern that has a definite structure. Imagine you could shrink yourself down to be a tiny iron filing. Wherever you are in the space around that magnet, you feel a push or a pull in a particular direction. If you mapped out every point in space, wrote down both the strength and the direction of the force you'd feel at that point, you'd have mapped out what we call the magnetic field. The field is a description of the condition of space caused by the magnet. This is a revolutionary idea. Not the magnet acting on the iron directly, but the magnet creating a field, and the field acting on the iron. The field is the middleman, the field is real. And the same goes for electricity. A charged object creates an electric field in all the space around it. Another charged object placed in that field feels a force. The interaction is mediated by the field. Newton's action at a distance, that mysterious idea that one object could just know about another object across empty space, gets replaced by something more satisfying. Local action. The charge acts on the field next to it. The field next to it acts on the field a little further away, and so on, until the influence propagates outward. This is a revolutionary idea. Not the magnet acting on the iron directly, but the magnet creating a field, and the field acting on the iron. The field is the middleman, the field is real. And the same goes for electricity. A charged object creates an electric field in all the space around it. Another charged object placed in that field feels a force. The interaction is mediated by the field. Newton's action at a distance, that mysterious idea that one object could just know about another object across empty space, gets replaced by something more satisfying. Local action. The charge acts on the field next to it. The field next to it acts on the field a little further away, and so on, until the influence propagates outward. Now here comes the big leap. The person who took all of Faraday's physical intuitions and turned them into a precise, complete mathematical theory was James Clerk Maxwell. And what Maxwell wrote down in the 1860s, 4 equations, now bearing his name, is, to me, one of the crown jewels of human thought. Let me tell you what Maxwell's equations say without writing them out in full. Don't worry, I'll give you the ideas. Light humor. The first equation says, electric charges are the sources of electric fields. Positive charges push the field outward. Negative charges pull it inward. Simple enough. The second equation says there are no magnetic charges. Magnetic field lines always close on themselves in loops, no monopoles. That maddening property of magnets I mentioned before, it's built right into the theory. The third equation, this is Faraday's law in mathematical form, says a changing magnetic field creates an electric field. If the magnetic field is varying in time, it curls an electric field around itself. And the fourth equation, this is Ampere's law, with a crucial correction by Maxwell, says a current of electric charges, or a changing electric field, creates a magnetic field curling around it. Look at equations 3 and 4 together. A changing magnetic field creates an electric field. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. A changing electric field creates a magnetic field. Let the cycle sink in. Do you feel what's happening? You have a self-sustaining cycle. If you disturb the electromagnetic field somewhere, if you shake a charge, if you cause a disturbance, that disturbance can propagate outward through space all by itself, carrying energy, traveling as a wave, with each oscillating electric field generating a magnetic field, and each oscillating magnetic field regenerating an electric field on and on, leapfrogging through space. Think of it like a line of dominoes. But instead of falling and stopping, each domino knocks over the next one, which simultaneously stands the previous one back up again. The disturbance keeps moving. It never dies. It travels outward forever, unless absorbed. Maxwell calculated the speed at which this wave would travel. He used the known values of 2 electrical constants, constants that experimenters had already measured in the laboratory by studying static electricity and magnetism. And when he plugged them in, he got a speed of roughly 300 million meters per second. That's about 186,000 miles per second. That's the speed of light. Maxwell knew the speed of light. It had been measured by that point. And here's what he wrote. and I think it's one of the greatest understatements in scientific history. We can scarcely avoid the conclusion that light itself is an electromagnetic disturbance in the form of waves. Light, the thing you use to see, the thing that warms your face on a sunny day, the thing that painters have tried to capture for centuries. That's an electromagnetic wave. Maxwell didn't just unify electricity and magnetism. He told us what light is. From two seemingly unrelated phenomena, playing with charges and magnets on a laboratory bench, out pops the nature of light. That's what I mean when I say physics is beautiful. Now, light isn't just visible light. That's a tiny sliver of the full electromagnetic spectrum. The same equations, the same physics, predict waves at all frequencies. Longer wavelengths give you radio waves. Hertz demonstrated their existence in 1887. About 20 years after Maxwell's equations, go shorter and you get microwaves. Shorter still, infrared, which you feel as heat from a fireplace. Then the tiny band of visible light our eyes evolved to detect. Then ultraviolet, the stuff that gives you a sunburn. Then X-rays discovered by Ørsted in 1895. And at the shortest wavelengths, gamma rays, all of it, from a radio wave hundreds of meters long to a gamma ray smaller than an atomic nucleus, is the same phenomenon. Oscillating electric and magnetic fields, traveling through space at the speed of light. The only difference is the frequency of oscillation. Imagine you're a surfer on the electromagnetic ocean. Radio waves are the long, slow swells that carry you gently up and down. Their crests are maybe a kilometer apart. Visible light waves are like tiny ripples, where the crests are only about 0.5 of a meter apart. Gamma rays are the most violent, furious choppiness imaginable, crests spaced closer together than an atomic nucleus. But all of them are waves on the same ocean, obeying the same laws, moving at the same speed. Now let me come back to something I glossed over. Why does any of this affect the stuff in your everyday life? You said at the start, I said, that electromagnetism is behind almost everything. Let me make good on that claim. Consider the chair you're sitting on, or the floor beneath your feet. You feel solid, right? Like you're resting on something hard. But here's the truth. The atoms in the floor and the atoms in your body never touch in the way billiard balls touch. What you call touch is actually the repulsion between the electron clouds of atoms, an electromagnetic repulsion. The normal force that keeps you from falling through the floor is electromagnetic. Friction is electromagnetic. The strength of every material, wood, steel, glass, flesh, comes from electromagnetic bonds between atoms and molecules. When you see colors, it's because the electrons in the molecules of paint or skin are absorbing some frequencies of light and reflecting others, electromagnetic interaction at the atomic level. When you smell something, molecules interact with the receptors in your nose through electromagnetic forces. When your nerve cells fire, carrying signals from your eyes to your brain, that process is driven by electrochemical gradients, the movement of ions across membranes, which is, again, electromagnetism. Your brain is running on electromagnetism right now, processing these words. Why pause, and then there's technology. Every electrical motor, in your refrigerator, in your washing machine, in every electric car, works by using magnetic fields to push on current-carrying wires. Every generator that produces the electricity powering your home works by moving a coil of wire through a magnetic field, using Faraday's induction. Every radio, every television, every radar system is sending and receiving electromagnetic waves. Every telephone. Well, the telephones I knew used electromagnetic principles to convert sound into electrical signals and back. The laser, invented in 1960, in my own lifetime, which still strikes me as extraordinary, is a device for producing an extremely organized, coherent electromagnetic wave. The laser works because we understood electromagnetism deeply enough to control how atoms emit light. So when I say electromagnetism is behind almost everything, I mean it. The exceptions are gravity, which holds planets in orbit and keeps you from floating off into space, and the nuclear forces, which govern the interior of atomic nuclei. But everything at the human scale, everything you touch and see and smell and taste, is electromagnetism. Now I want to pause and get a little philosophical, or rather, I want to get unphilosophical in the way that only physics can make you. There's a question I get asked sometimes: what is an electric field, really? What is it made of? And I want to be very careful here, because the temptation is to give a satisfying sounding answer that isn't actually honest. Here's what I can tell you. The field is a mathematical object that tells you at every point in space and at every moment in time what force a test charge would feel if you placed it there. It's defined by its effects. We can measure it, we can calculate it, we can predict with exquisite precision everything it will do. We know its laws. In that sense, we know it completely. But if you ask me what the field is made of, what it is in itself, in some deeper metaphysical sense, I have to tell you I don't know. And more importantly, I'm not sure the question has a useful meaning. When we ask what something is made of, we usually expect to be told it's made of something smaller and more familiar. But at some point, that chain has to end. At some point, you reach a description of nature that can only be taken on its own terms. The electromagnetic field is real. It carries energy. It carries momentum. It can exist in the absence of charges, but it isn't made of something else in any way that physics currently knows how to express. This used to bother me when I was younger. I wanted a mechanical model, ether, vortex tubes, little gears in space, something. But the history of physics is the history of learning to be comfortable with descriptions that are complete and accurate without being visualizable in classical terms. The field is what it is. We know its equations. That's not a failure, that's a success. Perhaps. But successful. Now let me tell you something about Maxwell's equations that I find personally astonishing, because I think it gets at something deep about the nature of physics. In 1905, Einstein was thinking about what Maxwell's equations implied about moving observers, about what happens if you're moving very fast and you look at an electromagnetic wave. And what he found was that if Maxwell's equations are correct, and if the speed of light is the same for all observers, as the equations imply, then the whole framework of space and time that Newton had given us has to be wrong. Time isn't absolute. Lengths aren't absolute. Simultaneity isn't absolute. Special relativity wasn't invented to patch up some crisis in physics. It was, in a deep sense, forced upon Einstein by electromagnetism. Maxwell's equations already contained relativity. They knew about it before we did. Imagine two people on ice skates, facing each other. One throws a ball to the other, the thrower recoils backward, the catcher recoils backward. That's like a repulsive force. Now imagine they're throwing and catching boomerangs, objects that come back, and somehow the exchange pulls them together. That's roughly the picture of attractive electromagnetic forces at the quantum level. Absurd sounding? Yes. But the mathematics works, and the predictions match every experiment we've ever done. Here's another thing I love about electromagnetism. It has a deep connection to a fundamental principle called gauge invariance. But I don't want to lose you in abstraction, so let me just say this. The laws of electromagnetism have a certain kind of symmetry. You can redefine certain quantities in a particular way and the physics doesn't change. And it turns out that this symmetry, this invariance, is not just a mathematical curiosity. It's essentially what forces electromagnetism to exist. If you insist on a certain kind of symmetry in your theory, you're led, almost inevitably, to the existence of a field with properties just like the electromagnetic field. The force arises because of the symmetry. When I was learning physics, we first derived the laws from experiment. We found out what the laws were, and then we were amazed by the symmetry we found. But I've come to think you can almost run it backwards. The symmetry is the deeper thing. The force is its consequence. Isn't that strange? Isn't that wonderful? The force that keeps the lights on, that lets you see your hand in front of your face, that makes your heart beat, it exists because of an abstract mathematical symmetry in the laws of nature. Nature is not just following rules. Nature seems, in some deep way, to care about beauty. Pause, or at least, the things we find beautiful, symmetry, elegance, economy, turn out to be deeply true. We started with a magnet and a nail, with the ancient mystery of things acting on each other across empty space. We found that electricity and magnetism, two apparently separate phenomena, are aspects of the same underlying reality, and that their relationship is mediated by something real and physical, the electromagnetic field. We found that Maxwell's four equations describe this field completely, and that as a consequence of those equations, there should be electromagnetic waves traveling at the speed of light. And then we found, and this still amazes me, that light is an electromagnetic wave. That optics and electricity and magnetism are all one subject. That the spectrum stretches from radio waves to gamma rays, all the same thing at different frequencies. We found that electromagnetism is responsible for almost everything at the human scale, every chemical bond, every material property, every sensory experience, every piece of electrical technology. We found that electromagnetism, taken seriously as a mathematical theory, contains special relativity, and we found that at the quantum level, the electromagnetic field is made of photons, and that the entire structure of the theory can be understood as arising from a deep symmetry of nature. That's not bad for a phenomenon that started with rubbing amber on fur. That's what physics is for. Not to remove the mystery, but to reveal the mystery more clearly, to show you that the world is not less strange than you thought. It is far stranger, and that its strangeness is precise and lawful, and in a certain sense beautiful. The nail still jumps toward the magnet. After all these years, and I still want to know why. Thank you.